Hello, my name is Raymond Mule, and for my project, I did MESFETs. MESFETs, or metal semiconductor field effect transistors, are very similar to the other FETs in the way that they operate, such as depending on the amount of gate voltage you put into the device, depends, sets the current on how much current is able to flow through the device. Uh, One main difference, though, is the Schottky gate barrier, which will be explained more in depth in the next slide. Uh, and then MESFETs are typically used for higher frequency devices, such as cell phones, satellite receivers, and microwave devices. Now onto the Schottky gate. The Schottky gate or barrier is a solid-state semiconductor diode in which a metal electrode and an N-type semiconductor form the diodes of an MS junction, giving it two major advantages over traditional PN junction diodes: a faster switching speed and a low forward bias voltage. Hence, that's why MESFETs are more used for higher frequency devices. So for my NanoHub simulations, I decided to set a baseline simulation so I could compare my future test to this one. So as you can see, the MESFET type is N-type. The channel material for MESFET operation is silicone. The channel length is 0.3 micrometers. The source region length is 0.1 micrometers. Gap length 1 is 0.1 micrometers. Gap length 2 is 0.1 micrometers. Drain region length is 0.1 micrometers. Body junction is 0.2 micrometers. And substrate thickness is 0.8. Onto the doping levels. For the source region doping, it's 1 times 10 to the 20th centimeters cube. Same for drain region doping, and then channel region doping is 1 times 10 to the 18th centimeter cube, while substrate region doping is 1 times 10 to the centimeters cube. So these are the graphs that I did. So I mainly went over the electron density and hole density at equilibrium, and then I went over how gate voltage affects the max current that could flow through the device. So the electron density that I got at 0.3 micrometers is 2.98 times 10 to the 15 centimeters cube, and the hole density that I got is 8.9 times 10 to the 4 centimeters cube. As for current, at a gate voltage of 0, I got 2.6 milliamps. At a gate voltage of negative 0.5 volts, I got 2.5 milliamps. At negative 1 volts, I got 2.4 milliamps. At negative 1.5 volts, I got 2.3 milliamps. And negative 2 volts, I got 2.2 milliamps. And all of these values are taken at a drain voltage of 2 volts. Now on to my test 1. So for test 1, I only wanted to change the dimensions of the device. I didn't want to touch with the doping levels, so I just wanted to see what happens. I also changed the MESFET type to P-type to see what would happen as well. So for obviously MESFET type is now P-type. The channel material for MESFET operation is silicone. Channel length is now 0.4 micrometers. Source region length, gap length 1, gap length 2, and drain region length are now 0.15 micrometers. Body junction is 0.35 micrometers, and substrate thickness is 1 micrometer. So for test 1 output, so electron density at 0.4 micrometers is 2.89 times 10 to the 11 centimeters cubed, and hole density is 1.18 times 10 to the 16 centimeters cubed. These density values were a lot closer than I expected. So I'm not assuming, but the dimensions, the change in dimensions is most likely the reason for these electron densities being so close to each other. And as for the current and gate voltage, at a gate voltage of 0 volts, it's 4.7 milliamps. At negative 0.5 volts, it's 4.8 milliamps. Negative 1 volt is 4.9 milliamps. Negative 1.5 volts is at 4.9 milliamps. And negative 2 volts is 5 milliamps, all at a drain voltage of 2 volts. So it seemed to have flipped from the baseline results to where the more gate voltage you put in, the more current that's allowed to go through. I'm also getting a lot more current that's able to flow through the device. So the flipping of the graph is, I'm assuming, since I changed the type from N-type to P-type, that's where I'm guessing the flip is from. As for the higher current flowing through the device, that has to be the change of dimensions that I've done. Now on to test 2. So test 2, I just did the opposite. I left the dimensions of the device the same, but I changed the doping levels, and I also changed the gate material for MESFET operation. I changed it to aluminum, which was originally just the work function at 4.87 electron volts. So I changed the source region doping to 5.5 times 10 to the 15 centimeters cubed, the drain region doping to 1.5 times 10 to the 16 centimeters cube, the channel region doping to 4.4 times 10 to the 14 centimeters cube, and the substrate region doping to 2.2 times 12 to the centimeters cubed. So for test 2 output for the electron density at 0.3 micrometers, I got 5.87 times 10 to the 14th, and for hole density, I got 3.6 times 10 to the 5th. The densities seem to be as far apart as they were in the baseline, so yes, changing the dimensions affects what density, or with the densities of electron and hole being closer or farther apart from each other, but the graph seems to be a lot smoother. There's not a lot of changes of density, drastic changes of densities over the position of the channel region length. So my guess is that since I changed level of dopings, it resulted in a smoother transition as you go like farther down the channel region length. As for current, at a gate voltage of 0 volts, you get 1.9 milliamps. At negative 0.5 volts, you get 2.4 milliamps. At negative 1 volts, you get 2.8 milliamps. At negative 1.5 volts, you get 3.2 milliamps. And negative 2 volts, you get 3.7 milliamps. Of course, all values are taken at a drain voltage of 2 volts. I'm unsure why NanoHub simulations decided to bring out like the graph a bit more than I wanted to. Since I had it set to 2 volts, since that's what it liked, anything more would really screw up the graph or make it far too big than I'd want it to be. But again, similar to the last test, the more gate voltage I'm putting in, the more current I'm getting out. But for test 2, it was still an N-type, so changing the levels of doping must also have an effect on how much current can flow through the device at the given voltage. But I'm also getting voltages more similar to the baseline outputs. So doping mainly affects the position or how the gate voltage reacts with the current, and then the dimensions mainly affect how much current can go through at a given time. My bad. There we go. For test 3, I changed everything. I changed levels of doping and the dimensions. So I changed the channel length is now 0.4 micrometers. Source region length, gap length 1, gap length 2, and drain region length are now all 0.05 micrometers. Body junction is 0.1 micrometers, and substrate thickness is 0.65 micrometers, and it's a N-type MESFET, and the channel material selected is silicon. For the doping, the source region doping is 9.2 times 10 to the 18 centimeters cubed. The drain region doping is 6.3 times 10 to the 18 centimeters cubed. The channel region doping is 4.4 times 10 to the 16 centimeters cubed. And the substrate region doping is 7.25 times 10 to the 13 centimeters cubed. And I left this metal gate work function at 4.87 electron volts. So for the output, at 0.4 micrometers, electron density is 3.38 times 10 to the 14th centimeters cubed, and hole density at 0.4 micrometers is 3.2 times 10 to the 5th centimeters cubed. So I'm getting similar differences of electron and hole densities that I got in the baseline and test 2 due to the changes of the doping level. But it seems that even changing the dimensions isn't decreasing the size, so I'm guessing changing levels of doping takes more priority than changing the dimensions of the device, and I also downscaled the device in this test rather than upscale, which I did in test one. So that is also a factor. Um, for the current and gate voltage chart, um, I'm unsure why I had it set to where it would go through 0 volts to -2 volts, but for some reason the simulation just gave me 0 volts and -1.5 volts, and I couldn't figure out how to get it back. So at a gate voltage of 0 volts, the ampage is 8.5 times 10 to the -4th amps, and at -1.5 volts, it's 6.2 times 10 to the -4 amps. So a lot less voltage or current that's able to flow through the device. So at a given time, uh, but it's going back to where the baseline was, where the more gate voltage you put in, the less current can flow through the device at a given time. Uh, so that is a result of changing level of doping and downscaling the dimensions of the device in certain aspects. So the purpose of this project was to see how the MESFET would perform once its attributes have been altered. What was found that changing the doping levels of the MESFET would alter how the gate voltage regulates current flow and makes the electron and hole density changes throughout the channel region less drastic. What was also found was that changing the dimensions of the MESFET decreases the difference of electron density and hole density. And this research is important because it helps engineers figure out how to alter the MESFET's attributes to the best suit their needs. So yeah, and then here are the references I used for my report. So thank you very much.